So we're going to begin with some important definitions, but I'm not just going to tell you the definitions. I'm going to get you to try to figure them out. So the first one is an angle in standard position. And you're not going to write down this stuff at the beginning, but I'm sort of going to set it up as a pattern recognition game. I'm going to draw an angle, and I'm going to say, yes, this one's in standard position. And I draw another one, no, this one's not. And I'm going to keep doing them until you think you've got a good definition in your head just from the examples. So for example, I could start with this angle, and that angle, we'll title these. This section will be the yes side, this section will be the no side, and this angle right here is in standard position. But this angle is not. Now, just giving you two examples isn't ever enough to really figure out what an angle in standard position is. Because after two examples, you go, oh, angles going one direction are standard position, angles going the other direction aren't. But then I go, well, what happens if I did this one going in the other direction? That is in standard position. So you start thinking, oh, maybe they're in standard position if they end in quadrant 1. So then I go, oh, that's the same one. That's a bad example. Oh, here we go. Here we go. This one in quadrant 1 is not in standard position. So we look at some more examples. This angle is not in standard position. But this one is in standard position.
Are we supposed to guess at it?
Or you think, have we got enough examples? You feel like you have an idea already? Okay. I'm just trying to think if I have any other ones that I could put that would be. Okay, I'll give you one and you tell me what you think of it. Yes or no? Okay. So you think you've got it? Oh, I've got it. No? Okay, what do you think for angle in standard position?
Angles in standard position, and the measurement of degree is based off the positive x-axis.
Okay, so the key thing that's in all of the ones on the yes side is they're all starting on that positive x-axis. Right? Notice that I tried some from the negative x-axis just because before that your definition might have just said from the x-axis. Right? So it's important for an angle in standard position to start from the positive x-axis. And it doesn't matter which direction it goes, right? Because this one went clockwise, this one went counterclockwise. We're going to find out that going counterclockwise, like the first example, is a positive angle. Going clockwise, like the second example, will be a negative angle. So let's write out that definition. You are correct. An angle in standard position, an angle is in standard position if it starts from the positive x-axis. Excellent. Definition number 1. And the reason we have a standard position so that if someone says, I have an angle of 72 degrees, you have an idea that's in quadrant 1, and we're all talking about the same thing, rather than one person thinking one angle in one place, another person thinking another angle in the other place. It just helps us communicate things clearly. Definition number 2. A reference angle. So in this one, I'm going to draw an angle, tell you the reference angle, draw an angle, tell you the reference angle, draw an angle, tell you the reference angle, and then you have to see if you can figure out the definition from having the answers and the question. So if I gave you 50 degrees, and that was an angle, and we'll often use theta for angles. When we're writing a reference angle for theta, we write a little r beside the theta to represent that's the reference angle. And in this one, the reference angle is 50 degrees. So after one example, your definition could be, oh, reference angles are the same as angles, because that works for our one example. But example 2 here, if I give you 100 degrees, well, arrow's a little bit off, then my reference angle would be 80 degrees. Next example, we'll go, okay, we're going to go 265 degrees, almost 270 to the edge there. My reference angle is 85 degrees. And now I'm going to go, ooh. What angle would that be? Because this way I can hypnotize you a little bit, like, ooh, you like math, you will do your homework. See, you're going to have a much better mark now that I did this example, because that little hypnosis is going to work. I can feel it. Oh yeah, it would be, what would it be, 360, 720, another 180 would be 900, maybe another 30 degrees. This is 930 degrees. Okay, reference angle would be 30 degrees. Oh, very cool. So now we have to see, is that enough for us to get an idea of what a reference angle is? Oh, we only did positive examples, right? It's always good to be a little bit negative in math class. Here we go. If this angle is negative 40 degrees, your reference angle is 40 degrees. Okay, so what's our definition of a reference angle?
The remaining degree space to the nearest positive axis. Well, I guess it shouldn't say positive axis, but I guess positive degree to the nearest axis from like whichever quadrant it is.
Okay.
That was a bit jumbled, but
Little bit. It's a positive angle. Okay, that's good to notice. And you said to the nearest axis. Well, I did this example 265 because you're only 5 degrees away here. That's the nearest one. The nearest x-axis, right? So if we go and since we wrote our reference angles in degrees, there's the nearest x-axis. Here's the nearest x-axis. If this is 100, that's 80. Here's the nearest x-axis. If it's 265, you'd have to go back 85 to it. Even though this one I do like this because that y-axis is going to look so tempting. You're going to be like, oh, the y, look at how close it is. Why don't I call my reference angle 5 degrees? Because it's just so close. No, you have to go back to the nearest x-axis. And here, all the way around, we were at 900 here and 30 more. This is 30 degrees there. And here, this is 40 degrees. So for our reference angle definition, a reference angle is the positive angle to the nearest x-axis. What if I did 270? What would your reference angle be? It would be 90. Because it's 90 degrees whether you go to one x-axis or the other x-axis. So in that case, and what happens if I did 180 degrees? The reference angle would be 0, because you're already on the x-axis. So you don't have to travel anymore. Okay. So what you notice that we try to do, or what I try to do with an example like this, is go through all the sort of easy, regular kind of questions. Then 270 and 180, where it feels a little bit different, we try to look at those examples. And then I also try to point out the ones where you're going to be most tempted to make mistakes, like, oh, it's so close to the y-axis. I'll be tempted to do that. Now, why do we need reference angles? Oh, this is trigonometry is just a good unit. So, but some understanding of reference angles and where they come from. So if I pick an angle that you memorized from last year in grade 11, like 30 degrees, okay, and then on that I say, well, obviously that would have a reference angle of 30 degrees. If I look in quadrant 2, I could do what angle to also get a reference angle of 30 degrees? 150. If I would go to quadrant 3, and I also wanted a reference angle of 30 degrees, I'd have to go 180 plus 30, 210 degrees. And in quadrant 4, if my reference angle was 30 degrees, my angle would be 330 degrees. Okay. So for example, test your memory. Do you remember what sine of 30 degrees is from last year? 1/2 or 0.5. What that means, okay, SOHCAHTOA, how many people remember that? How many people like, oh, I remembered it after you told me? I kind of remember it. I knew one of them was 1/2. I just didn't remember which one. That's okay. Sine of 30 degrees is 1/2. That means since sine is opposite over hypotenuse, if I drew, can I extend this forever? If I picked any point and drew a line straight down, and I measured the length of that line, say I measured it and it was 2 centimeters, then I would know that the hypotenuse here would be 4, because 2 over 4 reduces to 1 over 2. And every time you have 30 degrees, this will always happen. If you picked where it was 1, then this would be 2. If I chose 3, then that would be 6. And it doesn't matter where you pick. If you pick it and measure it and it's 2.18, you double it, you would get 4.36. Wherever you have it, that ratio will always stay true. Now, the important thing about reference angles is that if I always draw a line back to my x-axis, can you see I make exactly the same triangle here with 30 degrees. I would make 2 and 4. And so in trigonometry, when we go beyond 30 degrees, we say, well, sine of 150 degrees is also 1/2, because if we look at the triangle that's made with the reference angle, it's the same triangle. That's the reason that sine of 30 and sine of 150 are the same. And then when you went to sine of 210, it makes the same triangle again. But what happens in quadrant 3? Do you remember this? That it's negative. So we have some quadrants that are positive, some that are negative. You might remember labeling your quadrants like this, maybe calling it the cast rule, so that you recognize all of them are positive in quadrant 1. In quadrant 2, sine was positive, but the other ones were negative. In quadrant 3, tan is positive, the other ones are negative. In quadrant 4, cosine is positive, the other ones are negative. Now, part of the reasoning for the negative is sine is opposite over hypotenuse. Now my opposite side is going down. So that is part of the reason why it's negative. We're going to get an even better reason later on in class today when we look at how sine, cos, and tan are related to the unit circle. Okay, so there we go. That explains why it's negative. 330, same triangle. So sine of 330 degrees is also negative 1/2. So the powerful thing in trigonometry is if you can find the reference angle, then you can do all your trigonometry with that angle and then translate it back to whatever angle you're dealing with. So even here, right? Look at this, okay? Going back to the hypnosis one where you're liking math again. Sine of 930 degrees. If you type that into your calculator, okay, unless we did a mental math error in drawing it, sine of 930 degrees, check my mode, I'm in degrees, gives me negative 1/2 as well. All based on that reference angle. Whew. A little bit nervous there, pushed enter. I could have been telling all the wrong things if the calculator said a different answer. Then I'd be like, okay, you guys better go home. But too bad, we can keep going. Okay, so that's how the reference angle is related to different angles in different quadrants and why it's so important. Next definition, last definition in this section. Coterminal angles. You guys have been really good at getting these definitions. Should I try to make them trickier? Let's see here. Coterminal angles. I will give you statements, and you have to try and figure out if you can figure out the definition of coterminal angles. For example, 30 degrees is coterminal with 390 degrees, but not 150 degrees. So it is coterminal with 390, but not 150. 200 degrees is coterminal with negative 160 degrees, but not positive 160 degrees. And I'll give you two more. 1000 degrees is coterminal with 1360 degrees. Oh, and I'll give you an example that's not helpful. 1111 degrees happens to be coterminal with, oh yeah, perfect. This shouldn't help you whatsoever. So the last one is true, but wouldn't be helpful for figuring it out. But we have to see if we can use the first three and the patterns there to come up with a definition of what coterminal is. Okay, the reference angle is the same, that's true, and it's in the same quadrant, which is important because 150 has that same reference angle, but it's somewhere else. In other words, if I drew 30 degrees, there's 30 degrees, and then I drew, oh, I'll label it 30 degrees, and then I drew 390 degrees, that's what it would look like. So they have the same reference angle, and they end in the same quadrant. Okay? We can simplify that definition by just saying they end at the same place. Okay? In fact, our definition is going to use another definition. Here we go. Two angles if they share the same terminal arm. That means that they end at the same place. And in fact, of all the definitions we've learned so far, this is the best one using the English language. I love those definitions where the definition itself tells you what it is. Coterminal. Terminal is the terminal arm. Co in English often means to share. Okay, so you've got coexist, things that exist in the same place. Cooperate. You operate together and you work together. You sort of share that. A lot of English words that start with co means that you're sharing something. Okay? Co-ed sports team, something like that. Not all words that start with co share things like Coca-Cola. I guess you're supposed to share a Coke with your friend. They had a whole, maybe that's, who knows. Okay, so that is coterminal angles. And so if you knew that sine of 30 degrees was positive 1/2, you would also know that sine of 390 degrees is also positive 1/2 because they're exactly the same ending place. They're not the same thing, right? Because like 0 degrees and 360 degrees, they end in the same place, okay? But if you're like in a ski competition and you're like, oh, instead of doing a 360, I'm going to do a 0 because it's the same, you won't get as many points. You'll go down the hill, woo, and land, and everybody else will be like, okay. There was, oh, is it the last Olympics? There were the last Olympics where there was a competitor in one of the ski jump things, and she, in order to qualify for the Olympics, you just had to go to enough competitions and get enough points. And if you made it to the bottom of the hill, you always got the bare minimum amount of points, and if you did that in every single race, you could go to the Olympics. So it was one of these ones with a half pipe where like they're going up the side, they're doing all these twists, and then you got to this skier, literally all she did was she went up and then down the other side and then like just back and forth and made it to the bottom, and she was in the Olympics. But, you know, I don't even think she got last place because she made it to the bottom and some people didn't make it to the bottom. But no tricks whatsoever. So yes, it is different if you were doing 0 degree trick or a 360 or a 720 or a 1080. It would be much more impressive. Usually when I tried those things, I'd come up with some weird angle like a 223, and that's just doesn't land well. Okay. All right. So those are our main definitions, and some other things that we get introduced to. So your notes on that same page have examples of coterminal angles and reference angles and which way a direction. Here's a whole bunch of coterminal ones. So if you like to highlight things in your notes, you can go like, or if you wish your highlighter worked, never mind. You could highlight the coterminal definition in your notes as well. Oh, there it is. There we go. Highlighter's working. Okay. Oops. All right, so we've got all of our coterminal angles, and we can go to example 1